episode from the favorite artist electronist, Mr. Q12. So a long time ago, now it's 2026, so in 2019, I made a project. It was called LED Wings project. It means that thing on the wall that is interrupting the light in the room, pretty much. When I'm reaching with my hand to a sensor, I'm not touching anything. After that project in 2019, I built this remote control that you see it in my hand here with its orange LED. And this was, it says here 5 years ago, so it must have been later than the project itself. In 2021, I built the remote control. And immediately after I made this remote control, I really wished to have two of them. But this remote control, I built it around these batteries. You can actually see the battery here is a circle, and there is another circle there. I can actually show you. So this is how it's looking from top. And you can see it here on the table. It's right here with two batteries, and I built it with matchsticks on cardboard, pretty much. That's the design, and I built a remote control around these two batteries, pretty much. But those batteries, they were the only ones I had at that time that were powerful enough, I believe. It's 3 volts battery, lithium cell, it says. CR2450, it says there. 3 volts. And I built all this remote control around these two batteries. And I really wish to make another remote control. So this was the first one and a second one to have. One here on my computer and one in the back, on the table in the back where I'm working there. And sometimes I need to close the light and I have to lift my ass from my chair and actually go switch the light on my wall. So it was a very good idea to have a secondary remote control. And this project is about that idea that I started with, and it remained with me a very long time, all this time. And I never had time to put it in practice. I only built this remote control with a PIC microcontroller, PIC 12F508, and that's it. It remained like that as the status quo all the time. Only one remote control here at my computer desk, and that's it. No secondary remote control that I really, my soul was crying after it. It really wanted it. But I never find time to build it. So this is all this movie is about. I hope it's clear now. And pretty much I had to make a new design based around 555 timer. As you can see here, I'm using two timers, two 555s, and I couldn't make it the same as with the PIC microcontroller as the first one I made it because I lost everything. I didn't document the making of the first PIC microcontroller remote control. I don't know what happened. I lost every data. I lost even the files for the PIC microcontroller. It's a big probability that I still have the file from the PIC microcontroller when I program it. I searched for it in my computer and I didn't find it at all. So I decided to use 555s. This was actually a very old idea. I did plan it for a very long time, but I didn't know how to do it. So this is my concept, this is my taking, this is my design using two 555s. Not absolutely 100% because I did get some inspiration from internet, of course. I did look on various 555 circuits, but I didn't find anything quite like what you are seeing here with these two 555s. I did find other types of circuits, but not exactly like this one, this final stage that you are seeing it here. So I didn't copy this circuit from internet. I developed it, I thought of it. It took me a couple of days of tryings and errors, a lot of errors, believe me. It didn't work from the very beginning. Very late I figured out the errors that I was having, to remedy them and to tweak the circuit to work as I needed and to make the behavior like you are seeing right now with this on and off train of pulses, pretty much. That was the idea. And like I said, I had this idea for a very long time, but I didn't put my head to it. I didn't stop and think seriously about it. But this is the circuit that I'm having right now, and it's working perfectly in this simulator. All the data that you are seeing here, as you can see, is tested in reality. I actually built the remote control following this design, this circuit that you are seeing here, but I tweaked in reality the values of the resistors and the capacitors because this, like I said already, this circuit in this simulation had many revisions, and I changed it a lot until I balanced what I'm seeing here in the simulator and what I was getting in reality. Right now, this simulation, what you are seeing here is having the exact values as I'm having in reality. It's not different. So you can copy this circuit and tweak it yourself if you want. If you want to build yourself a remote control like this, and it will work with minor tweaks from your part if you want. These are the port values, the resistor values pretty much. Here I'm using 4 potentiometers, port 1, 2, 3, and 4, and I'm tweaking them to calibrate exactly how long and how short the output pulse. So that was the original case around those batteries, and now those batteries are no more. They depleted entirely. I had a stack of 3 batteries, 9-volt battery, which you are seeing it right now. Here is the battery inside this case. So I took out its board with the PIC microcontroller and I rewired everything on top, or better said, around this 9-volt battery. So what you are seeing is my new remote control around this 9-volt battery. Because the old remote control, its batteries were depleted. It was working intermittently and I had to get rid of it. And this 9-volt battery that I'm having here is actually from a multimeter. I have like 3 multimeters with 9 volts battery inside them. And I have left with 3 9 volts battery that they got depleted in those multimeters. And the multimeter itself doesn't work correctly when the battery is getting beneath certain threshold, and I have to change the battery. And recently I changed the battery with a fresh one in my multimeter, but this one and another two remains with 5 volts in them pretty much. And I said, well, it's time to change the entire remote control and to build it around this 9 volts battery. So this is the new battery, the new remote control. It is actually the old one, but with a new battery pretty much. And this is what you are seeing right now on my table. I also changed the LED. It was having a blue one, and I changed it to test it, and it's working fine with this one as well. I tested the 3mm LEDs and it didn't work at all. Only with 5mm diameter infrared LED is working correctly. I don't know what is the deal. I believe the 3mm LEDs are for very short distances, while the 5mm LEDs, like you are seeing right here, are for way longer distances, like a couple of meters at least. So they are better suited for distance, from my observations and from my components that I have. So I have this circuit diagram to pulse modulate PWM with 555. You can see there for driving motors or MOSFETs, whatever. And I tried with a PWM to control my infrared receiver on my wall, and it didn't work with a PWM with a single and simple signal like this. For some reason, it didn't work at all. I tried, I think, 1 or 2 555 schematics a bit more simpler than this. Probably something like this. My infrared sensor on the wall didn't give any sign of doing anything with this type of circuit. So this is a very basic circuit. It didn't do it. And then I start to think, well, that's a problem, because if I cannot use a very basic signal like this, what can I do? And I got panicked about it. And the next idea to search all the documentations that I had about this little board with the PIC12F508, and I didn't find anything, like I said already. And then the next step, logic step, I said, well, I should actually probe it. I put it under my oscilloscope, and lo and behold, I get the code pretty much what is inside that PIC microcontroller on its output. Yeah, I believe this was the output. It's pin 7 through this resistor directly onto this infrared LED. What is remarkable here, by the way, this capacitor here is not burnt or anything, it's just dirty. So what is remarkable is how few components are required, and the complexity is not in the hardware, but in software. All the complexity is inside the chip. So that's the difference from a 555 circuit and a microcontroller. This is a very big difference. The cleanness of hardware with a microcontroller is very clean. But the biggest problem is that if you don't have the code, you cannot double the circuit again. You cannot copy it. Also is the problem of reprogramming it again, and it's a little bit not so pleasant to reprogram it again, even if you have the code. But in my case, I didn't have the code, so I had to find a new solution. I did thought using Atmega chips, because I have a ton of them, but I said, nah, it's too complicated. It's like programming a PIC. Well, not as complicated as that, because this is in Ensemble programmed, while Atmega is in a C type of language, which is way more easier to do it. But it's a bit of derange. It's not that convenient, you know. And I said, well, I will do it with the 555s if I can. So that's the idea that I had. And I said, well, I should probe the signal from the chip. And this is what is the result that I got on my oscilloscope. So you can see here the division is 200 microseconds per division. This is the division here, okay? And if we are counting how many divisions are here, 1, 2, 3, 4, 5, 6, 7. Probably this little bit plus this little bit is 8. So 8 times 200, it means 1.6 milliseconds. And this is exactly this number that I noted it here, is 1.6 milliseconds, exactly how this on duration is. And the off duration, if we are still counting the divisions, we have 1, 2, 3, 4, and a little bit. And this is 200 microseconds. 1, 2, 3, 4 times 4 is 800 microseconds, plus a little bit more is almost at the half, almost like 100. And it's already 800 plus 100 is 900 microseconds by the eye. You know, I didn't super calculate it, just by the eye, and it's good enough. It's around 900 microseconds. Literally, what I'm explaining right now, this is exactly what I did when I got this image on my oscilloscope. And I actually numbered all these high pulses. So this is the high pulse. Here, and I numbered them all, and it's, I think, exactly 30 pulses. I actually stay and number them. And that's how I got this data that you are seeing it here in my picture. All right. And I put it on a paper. This was the first data that I put it down very quickly while I was measuring everything. And then I remade here, I put it up, I made it a little bit more visual, pretty much, to see it, to understand it a little bit better. And this is a close-up of the actual pulse. And this is the same thing I did earlier. I literally look at division here. I have 20 microseconds per division. So each square that you are seeing here is height and width is 20 microseconds. Let's see one that is starting, this one here is starting exactly, you see, this is the division, and it's starting exactly at the division. And the on is exactly, the on state is exactly 20 microseconds, and the off state is a little bit less than 40 microseconds. So it's like 38 microseconds. And let's get back here. And you can see here is exactly 20 microseconds on, and I said 35 microseconds back then when I see it. So this is how I back engineered the signal from my programmed microcontroller that I did so many years ago, and I didn't know how the signal was looking like, because remember, a simple signal from a 555 didn't work at all. So this was a little bit a hack. I hack my microcontroller output pretty much. I'm looking inside my microcontroller and I'm seeing what I programmed inside it. And this is the pulse that was working absolutely perfectly all these years. It worked absolutely perfectly, and from a very respectable distance, like 5-6 meters like that, with this pulse that you are seeing here. Excellent. Is not super long distance, but is very good for the needs that I'm having. I'm standing on my chair and I'm switching my remote control and I'm opening or closing the light in my room. This is what it is doing. Next, I said, well, I have to simulate the same signal, but with two 555s this time. And I made this circuit here. It took me 1 day to make it, 1 or 2 days. I made a lot of mistakes. It didn't work from the beginning, from the start. Little by little, I took some breaks. You know, I watched a movie, and after a couple of 2 or 3 breaks, I look on internet a little bit on other schematics. I actually asked ChatGPT about this problem, and he was not good at all. It didn't help shit. But he did mention a diode, 2 diodes actually. He said to put the diodes somewhere, but I didn't understand exactly from his description where and how to put those diodes. But he did mention the diode, and it remained in my head. I was having a problem, a very big problem actually, from port 1 and port 2 here. If I was changing one or another, the pulse here, the length of the on state and the off state was synchronously changing. It was influencing one and the other. If I was making bigger the on state, the off state was making bigger automatically. If I was lowering the on state with it, the off state was lowering in the same time. So this was a very, very big problem without this diode here and here on both chips. And this diode saved my circuit, because with this diode here, I can change only the on state, but the off state to remain as I set it from port 2, and from port 1 I'm changing only the on state, how long the width, how long to be, and it's pushing everything else, you know, but is maintaining the off state. That's the difference. And also the same goes for the off state. If I'm changing the off state, it's changing the length, but the on state is remaining fixed, is not changing. So this was a very, very tricky detail that I didn't know about it, and I had to learn it, I guess. Also a very, very big and very interesting. I am amazed I didn't know it until this project here with the 555s. I'm commanding with slower pulses. This is the slow pulses. I'm mentioning here the on delay and the off delay. The big, pretty much this is on, is allowing all the small pulses. So this side here is one with on and off signal part, and this port 3 and port 4 is actually changing the signal structure. How much on and off is everything, and how many, pretty much, how dense to be the signal, or rare from this side. So I'm changing with 4 potentiometers. I'm changing everything. Yeah, absolutely everything I'm changing. A very, very cool detail I didn't know about it was from pin 3, from the output of this on and off delay, the bigger delays. This is the big delay and this is the small delay, pretty much. And from the bigger delay, I'm commanding from the output on pin 3 of this 555. I'm going to the reset pin and I'm keeping it low, the reset pin. This chip, when it's high, is activating pretty much this chip to create the burst of signals, like, and when this circuit is getting low like this, is literally switching off, because it's putting this reset pin to 0 volts, and it's switching off all these pulses, and I have a clean off state, pretty much, or off delay, whatever you want to call it. And I did it with other chips, but not with 555s. It's called cascading. I did it with a lot of other logic chips, like counters or gates, whatever gates. I cascade them one on another, but not with 555s. This is the first time when I'm cascading, and it's a very, very cool way of cascading 555s like this. Very good thing. You can actually command with a microcontroller this way on the reset pin of a 555. You can command with a microcontroller. You can command it with a logic chip even. Why not? A NAND gate, an AND gate, whatever gate you want. It's a very, very interesting pin, this reset pin. Until now, all my circuits were linking pin 4 to the high state, to the VCC pin 8, like this all the time. All my circuits that I did until now, I just use it like that, but never to be commanded when off and when on. That's it about the circuit diagram. Here is the infrared LED with a 100 ohm resistor, but you can put lower values if you want a bigger intensity to have more infrared light from this LED if you get lower resistance here. But be careful on the voltages. If you're using higher voltages and this resistor is too low, I don't know. It's a bit tricky. I keep it mine as a 100 ohm to be on the safe side. And this is a power LED, a simple LED that I use it in my older version, just to show me that I have power in my battery pretty much, and that my button is working when I'm pressing it, to actually see when I'm pressing the button to see something is lighting up, because the infrared LED I cannot see its light. Originally I didn't use this 2 capacitor, this 10 nanofarads and this 1 nanofarad. I had other values, and in reality actually I reached this value and this other value, and as you can see it says here tested in reality, and all these values are from reality. As you can see, the potentiometers here in the schematic, as they are random because I was testing here. But in reality, I switched my potentiometers. I took their values. I measured each potentiometer. I took it out. I built it on this breadboard with all these 4 potentiometers, as you can see, and I tweaked them and I measured them with my oscilloscope. You can see here the title. This is the signal with the 555, and this is another signal also with the 555. So this is the signal with the 555, and this one, the burst of 1.6 milliseconds on, and how much it was, like 900 microseconds off with the 555 is this one. And this one is the inner signal. And it's very important to have this signal, because if you don't have this specific signal, it will not work. If the signal is too big or too wide, or is not having the on and off exactly this, exactly this shape and form of the signal. As you can see, I'm using this infrared LED that is blue, not white, and I have only 2 of them. I don't have that many, and they are quite good, I may add, from America. And this is the actual boards, and I leave my finger as a reference to see how small everything is. These are SMD 555s, and I think at this stage I managed to complete both of these 2 boards, and I named them. This is A and this is B board. I also name it here A and B. So A is the big, the on delay and the off delay, and the B board is the small burst of the signal. I literally copied on my paper with the crayon on paper the same schematic that I made it in my simulator here. Here I mount these 2 boards, small boards, on this larger board, and I tested it. I tested the last output like I did on my breadboard, just to be sure everything is linked together, everything is connected together. And I was testing the last, you can see, B module. So this was the B module, and I probe it somewhere here. I probe it directly on its output, and I obtain the same, pretty much the same results as on the breadboard, and or in my simulator, pretty much 1 millisecond per division. And so this is 1 and almost half there. It's not the same as on the breadboard. I didn't use the exact same values that I measured from the potentiometers, but instead of this 190 kilo, I didn't have 190. I think I find 180 kilo for this specific one. I had 100 kilo for this. I don't remember this one and this one. They were a bit different, but still in the same ballpark. And I still got these beautiful signal shapes. You see, if this is 20 microseconds per division, I have exactly 40 here. 40 microseconds, and here exactly 20 microseconds. And a close-up here, and this is the battery, and here is another close-up. I'll make it full screen for you to actually see everything. This is the capacitors, 2 of them. We can actually read the numbers. 22 probably a kilo, and here is 56 kilo, and here is 100 kilo, and here is 180 kilo. Yeah, and this is the small diode, 1N4148. I didn't cut it. It's actually SMD diode like that. And this is the 555. And that's it for the components, for the close-up. And here I'm preparing the second board for the button. Here will be the infrared LED, and here will be the power LED with its resistor there, and here is the 100 ohm resistor for the infrared LED. I had to fight with the space because I needed to fit on this side of the battery, so that's why the cardboard that you're seeing here is this shape to fit exactly in this width and height of the battery. So this is one side here, and this one is on the back on the other side, so I'm using 2 sides of the battery. It's a bit weird, and I will repeat myself. You really need this specific pulse to command this specific infrared receiver. By the way, let me show you the receiver. I have 3 versions, actually 4, that are looking the same, and I have no idea which one I have. It's looking like this. This is the receiver that I got from America 5 years ago or something, or even more than that. And I took 20 pieces, as you can see here, of this model VS838, and it's looking very similar with what I have mounted on my wall. I also took 100 pieces of Actually, it's 50 infrared LEDs plus receiver, but those are shitty receivers. I'm not sure how good they are compared with these other ones. I think these ones they have a small microchip in them, and they are accepting this specific burst of signal. They are more special pretty much, but these are dumb. So these are very dumb, very stupid receiver. They can be influenced from any infrared light, indifferent of the signal model. You know, if it's a infrared light from the sun or from a flashlight, it will actually conduct. It's not a smart infrared receiver. It's a good receiver, I'm not saying no, but it's not a smart one. While these ones, they have a microchip in them and they are a bit more smarter. You need a specific signal to command them and to enable their output. This is the specific signal that you need to command them. After I discovered everything, after I decided to actually buy a couple of these smart ones, then I opened their datasheet. I started to search for them, and this is what I find. This one, I was having it for a very long time ago. Most probably this was the original that I had on my wall and that I tested with. But I think the other models that I'm having here are not that far away apart from that original one. Especially this VS838 that I commanded on AliExpress, and you saw it there. What it caught my attention is the angle. Reception distance is L0. It means right in front of it is minimum 14 meters, and if you are going to the angle of 45 degrees, I think this is L45, it means the distance is lower, like 6 meters. I'm usually 3 meters like that from my chair to the wall, and yeah, I'm fitting everywhere in each mode. Usually I'm pointing it directly, like L0 directly towards it. Yeah, like I said, this is the block diagram that what is having inside it. It's having a lot of processing thingy inside it. It's not simple or dumb. This is the most important. So after I discovered it myself with the oscilloscope and everything that I explained until here, then when I downloaded this data sheets for this specific model that I decided to buy it from AliExpress. Then when I looked a little bit more closer into the datasheet, I realized what I discovered with my oscilloscope there. They actually mentioned the high and low pulse. I'm not completely sure. Maybe this is different from my receiver. It's a completely other model. Let me check the other model here. From what I remember, it's pretty much the same thing. Oh, check this out. Here it is. 600 microseconds on the on state. The high, the on and off state here is also 600. Yeah, they are different. They're different, but it's not exactly like what I'm having here. Huh, very well. But I think they have some tolerances. There might be some tolerances. I'm not completely sure. And probably I fit in some tolerance somewhere. Yeah, they are not the same, exactly the same. They are, but they are relatively close. This is 400, between 400 and 800, and the other one was strictly 600. I think it's probably the same thing. But that's my realization. They are giving you some data about the high and low pulse, pretty much exactly what I discovered with my oscilloscope. Okay, pretty much that's it until here. And now I will present the actual remote control to see it functioning in reality. So right now, this is how it's looking. I don't have a cover yet. I have to build one. On this naked, I soldered onto the pins of the battery some contacts for the negative here and there, and for the positive here. I put this little LED there. When I'm pressing, is lighting up. It's connected directly on the battery. Voila. Yeah, you have to angle it directly to the sensor there. Let me show you the sensor. And this is the sensor here. So from this distance. And this is the sensor, as you can see. And it's brand new from America, from my friend. He gave me two sensors, one that I used, and this one as a reserve if I fucked up the first one. But I didn't manage to fuck up the first one, so I remained with it here. But I have no idea what brand it is, what number it is, what model. I don't know. And these are the small ones, the 3mm that I mentioned. They are not made for distance. They are not good at all. They are limited in distance. This is the actual LED that I got from America. Also two of them. With this special receiver. And this is my board, my prototyping board in the very beginning, that it helped me immensely figuring out the frequency to get to that specific frequency that I have it here. And this is the updated paper diagram. The PIC microcontroller remote control, like I said, I built it around this other 9 volts battery. I used a white scrapped infrared LED that I had it there from God knows where. I have no idea. This is not from America, it's just scrapped. And let's see it working. It's not having the range as this one is having. I'm not sure, maybe it's the battery. I think the battery is exactly the same because I measured them. And they have, both of them, they have 5 volts. I think the microcontroller or this LED is not the same quality with that one. I'm not completely sure. I blame the LED because I did use the PIC microcontroller remote control, exactly this circuit from this table, like with this one. So I think the LED transmitter matters a lot, the quality of it. But this is a bit more directional. I have, if I'm keeping it from this angle, it will not work. Or maybe it will. Let's see. No, it doesn't. It doesn't. I have to move somewhere there, and it will work like that. Yeah, see? So it's a bit more directional than this. I think this is the angle is more wide for the infrared, and this is a bit more shorter angle, like that. Somehow, I don't know how to explain, but from my position when I'm working at my computer, I'm using it all the time directly in front of the receiver, so there's no problem with this. This one is more versatile because of the wide angle. I buy 50 transparent infrared LEDs, most probably like this one. I will have to test them later, at a later date, and we will see how good they are compared with what I'm having here. I actually, on this remote control, I put this smaller infrared 3mm infrared LEDs. I put it here and I tested. They are very, very shitty. So unsoldered this one from here. I put the 3mm here and I tested it. And then I took it out and I put this one. Original LED was this one here, but I switched it to the new 555 remote control. Yeah, pretty much this is it. I hope you like everything I made here, and if you like it, please give a like, leave a comment, and I say goodbye to you. On to the next video project. Bye bye from your favorite artist electronist, Mr. Kutev.